Okay, so let's go ahead and take a look at the next section. So the next section is what we call graph interpretation. So you have to remember something from a previous unit. The previous unit where we took an equation and we found critical numbers, and then we figured out where f was increasing and decreasing, and relative max and relative min, and tangent line and point of inflection, and concave up and concave down. So how do you find the critical numbers of the function? Take the derivative, set it equal to 0. The f prime being bigger than 0 is where f is increasing, f prime less than 0 so the function is decreasing. Where do you have a relative max? Where it's increasing to decreasing. Relative min, where it goes from decreasing, this should be decreasing, to increasing. Oh, it's okay. Where f goes from increasing to decreasing is a maximum, and decreasing to increasing is a minimum. How do you write the equation of the tangent line? Find the derivative of a specific value of x, then use point slope or slope-intercept form. How do you find points of inflection? Take the second derivative, set it equal to 0, solve for x. Find out where the function changes concavity. So, where is f concave up? Remember, we talked a little bit briefly about this. I defined concave up as where the graph, so the derivative graph, is actually increasing. So f is concave down where the derivative graph is decreasing. Concave up is where the graph of the derivative is increasing. Okay? So you will be given a graph when you do this. Okay? And you do need to remember, you probably will need the fundamental theorem of calculus part 1 at some point. And then you have to remember that there is a fundamental theorem of calculus part 2, which we haven't talked about yet. But the fundamental theorem of calculus part 1 was taking the derivative of the antiderivative. Okay? Fundamental theorem of calculus part 2 is pretty obvious, meaning that if I took from a to b of f prime of x dx, that this would be f of b minus f of a. Take the antiderivative of the derivative and you get the original function evaluated at a and b. Okay? That is the fundamental theorem of calculus part 2. So now let's take a look at an example where I'm actually going to give you the graph. Hardest part about this is just knowing where everything is. Now, I will tell you something. In this particular section, it may not be a bad idea, if you haven't started doing it already, it may not be a bad idea for you to go through and take my video notes, like the filled out version, copy it down onto your notes packet, and then listen to the rest of this video. Okay, because then you can make other notes along the way without it taking a long time for you to go through and pause the video multiple times. So in my personal opinion, I would write down the notes first, even though you're not going to know kind of what it's talking about, and then I would go and fill it in. I don't know if I would go the other way by listening to the video first and then going and filling it in, because you might have to watch the video a second time. Okay, so, and I'm going to use my filled out version. I will use my filled out version to kind of illustrate what's going on. Okay. So, anytime you get a graph interpretation problem, it will say something like, let g of x be equal to an antiderivative in terms of f. And what the graph that they give you is not f prime. They gave you the graph of f. Okay. And so, if I want to compute g of 1, Remember what we do back in a previous class. You take that 1 and wherever the x is, you replace it. So in this case, my x is in the top. So my 1 goes in the top. So then I take my antiderivative from 1 to 1 of f of t. Well, remember, since a and b are the same value, then g of 1 is 0. Okay? Now, if we switch gears and look at g prime of 1, let's first find g prime of x. So here's my g of x. By the fundamental theorem of calculus part 1, when I take the derivative of this antiderivative, I plug in x in for t, and then I multiply by the derivative of x. So this becomes f of x, and then times the derivative of x, which is just 1. So this becomes f of x. So what's g prime of 1? Well, if 1 is where the x is, then I'm going to plug in 1 here. So what is f of 1? This is the graph of f. When x is equal to 1, I'm here, so I'm up at this coordinate point, which is 4. So since f of 1 is 4, then g prime of 1 is also 4. Okay, graph interpretation is really a difficult topic. So this is something where it's probably going to take you some time to fully understand how to do the graph interpretation. It's going to take you a little bit, where you're going to want to ask some questions. But again, every single thing that I do with this graph interpretation, I revert back to the unit where we were given the equation and asked you to find characteristics of the graph. That's what I do. So I don't look at the equations. I don't really look at the graphs. I try to interpret based upon what the question is asking, what I'm supposed to do if I were given the actual equation instead of the graph. Okay? And then once I think about what I'm trying to look for, then I go to the graph to try to evaluate. Okay? So now let's look at g double prime of 1. Well, at x equals 1, if I wanted to take the graph, g double prime of x is the same thing as f prime of x. So here's the graph of f. At 1, you have a sharp corner. So g prime, double prime of 1 does not exist because at x equals 1, there's a corner, which is not differentiable. Okay? So let's look at another couple of examples. And again, just like with the previous unit, what I'm doing is I'm really going through and trying to ask as many possible questions as I possibly can. So then that way, when you're faced with a new situation, hopefully we've at least done one example that looks like it. Okay? So now, let's find g of 4 and g of negative 2. So g of 4, so we plug in 4 in for our x's. So now I'm taking the antiderivative from 1 to 4 of f of t dt. Remember, this is the graph of f. So from 1 to 4, area, remember, a definite integral represents area under the curve. So what I have is I have the area of a trapezoid, an area of a triangle, and the area of another triangle. So g of 4 is equal to 1/2 trapezoid, 4 plus 1 times 1, plus my triangle, 1/2 base times height, so 1/2, 1 plus 1. And then anything that's below the x-axis is defined as negative area, so this is negative 1/2 base times height. And so g of 4 is going to be 5/2. Okay? Now, let's find g of negative 2. So I put negative 2 on the top. So g of negative 2, now what you notice is that my a value is bigger than my b value. So I need to flip and make that entire thing negative. So negative 2 on the bottom and 1 in the top, f of t dt. And then from negative 2 to 1 is this area of this big triangle right here. So g of negative 2 is equal to 1/2. My base of that triangle is 3 and my height is 4. So g of negative 2 is equal to 6. Okay? So now we talked about g double prime for a second, and we talked about g double prime I don't want to give away anything, even though you probably have it written down. G double prime of 3/2. So 3/2 is right about here. Now, when we are at 1, that's a corner. When we're at 2, that's another corner. So at 1 and 2, not differentiable. This, again, is the graph of f. When I want to say g double prime of x is equal to f prime of x, we know something about trying to find the value of the derivative, okay? And it's the mean value theorem. The mean value theorem states that if a function is continuous and differentiable, then the derivative at a specific value is equal to f of b minus f of a over b minus a. We can extend this idea of mean value theorem to evaluate what g double prime of 3/2 is. So g double prime of 3/2 would state, my variables are off. So g double prime of c would be g of b, g prime of b, minus g prime of a over b minus a. Remember that g prime, though, we defined in the previous example, g prime of x is the same thing as f of x by the fundamental theorem of calculus part 1. So that means that this is f of b minus f of a over b minus a. So when I look at 3/2, what I'm looking for is g prime of something to the right of 3/2, which is 2, minus g prime something to the left of 1.5 is 1 over 2 minus 1, which is the same thing as f of 2 minus f of 1 over 2 minus 1. And the reason why it is f is, remember, g prime is the same thing as f from the fundamental theorem of calculus part 1 in example A. Okay, so now f of 3/2 should be not f, should be g double prime. So g double prime of 3/2 is equal to f of 2, which is 1, minus f of 1, which is 4, over 2 minus 1. So that gives me negative 3. So g double prime of 3/2 is equal to negative 3. So let's go back for a second before we go on. G double prime of the function, you're either going to have one or two situations. One, you're going to have mean value theorem if it's somewhere in the middle between coordinate points, that's given. Or two, you're going to have does not exist, because it might be a corner, cusp, or discontinuity. Okay? So those are your two options for G double prime. So now, let's figure out some critical numbers. So g of x has critical numbers when g prime is equal to 0. We found in part A that g prime is equal to f. So if I want to know when g prime is equal to 0, I really want to know when f is equal to 0, which in this case are 2 coordinate points here and here of x equals -2 and x is equal to 3. Okay? And then we talk about g of x being increasing or decreasing. So g of x is increasing when g prime of x is bigger than 0, which is f. F is bigger than 0 when the graph is above the x-axis. So I've already colored it for you, which is on the interval from -2 to 3. G of x is decreasing when g prime or f is less than 0, which I already colored it green here, from the interval from 3 to 4. Okay? Where does g of x have a relative min and or a relative max? I only change here from increasing to decreasing, and so there are no values of x where the function changes from decreasing to increasing. So there's no relative minimum. G of x has a relative maximum where g of x changes from increasing to decreasing, which occurs at x equals 3. If I ask you whether or not where does g have a relative min and or a relative max, you have to tell me that there's no relative minimum. So you have to state both. Okay? So part G, where does g of x have a point of inflection? Well, in order to have a point of inflection, you have to change concavity. So you have to do part H before you can do part G. And so just know that typically on the free response test for College Board, they will put point of inflection before concavity, even though you're supposed to do whether or not it's concave up or down first before you identify points of inflection. So they will always probably ask you questions backwards for this. Okay? So first, let's figure out where it's concave up or concave down. This is where the definition kind of changed a little bit, and you have to remember what I kind of said in the previous unit where we defined concavity. So a function is concave up if f prime is increasing, meaning if I were to put tangent lines along the graph of f, and those tangent lines had positive slope, then the function would be concave up. Okay, so g of x is concave up from -2 to 1. Now, what about concave down? Concave down is where the slopes of the tangent lines are negative on the graph of f. So g of x is concave down from 1 to 4. Okay? Now let's switch examples just so that you guys can get an idea of maybe a free response question, because typically they have 3 or 4 parts to it for a graph interpretation. So new function contains 3 line segments. Let g be the function where it's the antiderivative. Find g of -1, g prime of -1, and g double prime of -1. So g of -1 puts -1 in the x, which means you're finding the area of this trapezoid that I already colored in. So 1/2 -2 plus a -3 and times the height, which is also 3. So you get 15 halves. Again, by the fundamental theorem of calculus part 1, g prime would be plugging in my x in for t and multiplying by the derivative of x, which is 1. So if g prime is equal to f, then g prime of 1, negative 1, is f of negative 1. And f of negative 1 is equal to 2. And then at negative 1 here, that's actually a sharp corner. So g double prime does not exist because f is not differentiable at that point. For the function defined in part A, find the x-coordinate of each point of inflection of the graph on the open interval and explain your reasoning. So g of x is concave up, where your slopes of your tangent lines are positive. G of x is concave down, where your slopes of your tangent lines are negative. So that means that there is a point of inflection at x is equal to 1, because it will change from concave up to concave down. Let h be a new function. To be clear about this new function, the variable is in the denominator. Find all the values where h of x is equal to 0. What that means is that I need this entire integral for a value that I plug in for x to give me a net worth of 0. So some things that you'll be able to know is that this triangle, this triangle, this triangle, and this triangle, all 4 of those triangles that are there, give you 0, because 2 of them are below the x-axis and 2 of them are above, and they're the exact same areas. So when x is equal to negative 1, I do all 4 of those areas of those triangles, and that gives me 0. Now, when you start going from 1 somewhere, so then another area that gives you a net worth of 0 is from 1 to 3. Remember that this is a fixed 3 here, so you can't change the 3. So I couldn't have gone on the left-hand side here because I can't change that top number from 3 to something else, which is why I only can go from 1 to 3, and then that gives me a net worth of 0. The only other one that works is when both a and b are equal to each other, which is when a and b are both 3. Okay? And now looking at this, for the function h defined in part C, find all the intervals for which h is decreasing. So here's h of x. H of x is decreasing when h prime of x is less than 0. So first, find h of x. So I need to flip and multiply my boundaries and make everything negative. And what you notice is that h prime of x is equal to negative f of x. So I want decreasing. So I want h prime being less than 0. H prime is the same thing as negative of f of x. So I want negative of f of x to be less than 0, which means that f of x has to be bigger than 0. So if this is the graph of f, where is f bigger than 0? F is bigger than 0 from 0 to 2. So h is decreasing on 0 to 2 because h prime is equal to negative f, which is less than 0. On the interval where negative f is less than 0 means that f of x has to be bigger than 0, because you multiply both of them by the negative, and then that flips the direction of the sign. Okay? And that is it for this lesson.